the axes, don't you have to have them all still originating from one point?
No, you don't. So
Okay.
Uriah just asked, do we have to have all the axes originating from one point? No. You could find, you know from the previous chapter, that we could find a moment about any line, right? So we're looking at, there's, I guess in this case, there is x, we wound up putting x prime, y prime, and z prime through each other, you know, they all were origin of B, but no, we could have done y prime here. We don't have to. Okay, they don't have to be coming from the same point. We're just finding a line in space. Okay, Uriah?
Oh, no, my hand's
You're
not.
okay? Okay, Santiago?
I think along the same lines, so you can move the origin anywhere, find a force or a moment, and then move the origin again to find something.
That's right.
Yeah.
Because you're not really moving the origin, what you're doing is choosing a line that you want to find the moments about. So I'm calling them x prime and y prime, but we could have called this line, you know, B, D. I'm finding the moments about line BD. It might have nothing to do with our x, y, or z axes. This is so great. Lucas, I gotta give you some extra points. What a lot.
It's kind of like the same thing when we were doing two-dimensional, where we would pick the point where we were rotating about, like, we wanted, there were two reaction
That's
points.
right.
We chose that point specifically so we would cancel out.
Exactly. So what Chelsea's saying is in a 2D problem, you got to choose the point you wanted to find a moment about, and it didn't matter which one you chose. That's the same thing for Santiago. For a 3D problem, you could choose any line you want. I happen to call them x, y, and z prime, but they could be called anything.
So maybe if we use the term origin, we should have one spot, but we can move it as much as we want. But if we want to,
Yeah, but we don't even
use
need to
anything. Yeah.
we don't even need to talk about origin. I mean, think about when you build something, like whether it's in Legos or a bicycle, there really isn't an origin, right? There's not really an origin. Origins are helpful for coordinates, right? We're not dealing with coordinates at all. Claire?
I'm not sure this question is gonna make any sense, but so like we have that bar, we're building it, whatever, it's like it's on the wall. So whatever moments are gonna happen, or forces are gonna happen in the different reactions and stuff, is not gonna change. It's always gonna be the same. So separating out and not having an origin and finding moments and stuff about different lines will not change. It changes the moment, but won't change it.
It doesn't change
You
the
know what I mean?
physical aspect of what's happening.
Yeah.
That there are reactions at the supports. There are, so we start out with, we have this bent bar, and actually, Evan, would you mind going, the paper towels next to the bathroom in the engineering lab is this bent bar. Karen had it built once, we should bring it in. So this bar, as an engineer, we chose this bent bar, we chose the connection of A and B, and we're resting the bar on the surface, the floor and the wall, and we're applying a 200, 300, and 400 Newton in that area. The reactions at the supports are going to be the same whether I analyze the moments about here or here or here or wherever.
That was my question. Perfect.
So you choose lines to find moments about that make it easier.
So you don't even need a manual.
You don't even need a matrix anymore. You don't even need to know how to divide. Well, I guess you do still have to divide. But I mean, it's the most minimal math, right? So what you're doing is you're using your static skills to minimize the math, which is really what we do in engineering all the time. We don't want to spend our energy, doing math. We want to spend our energy coming out with a better design. So here's our, here's the bent bar, although there's not a vertical surface for it to lean on. It's a little rusty now. So here's our bar.
So did you make that bar?
I did not. Karen had somebody, her friend who works in the machine shop at UCSC make it.
Because of the problem, or
Yes.
was the problem based on, okay,
No,
because
she
of the
made
problem.
the bar based on the problem.
Cool.
Yeah. So, did everybody get it? As engineers, we don't want to spend time number crunching. We don't want 3, 4 pages of engineering paper with numbers. We want to understand the physical of what's going on. So figuring out which axes to find the moments about. I feel like we all learned so much we could just go home now. No, we're not going to. No. Okay, so next problem we're going to do is this one that you did for homework. So check with the person next to you and see if you have the same forces drawn. And I'll start to draw them up here.
Figure this one out.
Good job with that idea. Okay, did I miss anything? So what's the connection at D? D? It's just a normal. In fact, I probably would just call it N instead of, because if I call something N and I get a negative at the end, I know that it can't be negative. You don't have to call it N, you can call it DY, you could call it D.
N sub D.
You could call it N sub D, yeah.
My only thing is, like for the BCD connection.
Okay, so let's label these free, I should label the free body diagrams, right? So let's label them so we can refer to them. So free body diagram, do you want to call it free body diagram 1, 2, 3, and 4, or do you want to label it by the member? Member? So BCD, free body diagram ABE, free body diagram CEF, and free body diagram total?
Yeah.
Okay, Sarah, which free body diagram?
So, BCD,
BCD, okay?
so I think it doesn't matter, but I ended up putting, BX and CX to the right and BY and C right.
That's fine, so you probably drew the free body diagram for this one first, possibly. And then when you went to B, you had to put these the other way, right?
Oh, I see,
Right?
okay, I just clicked, so if you have the separate free body diagrams, that B has to, the BX from ABE has to cancel out the BX.
That's right.
from- Okay.
If I put these two free body diagrams together, the B's have to cancel because that's where they connect. So looking at these two BX's, one is to be to the left and one has to be to the right. For the BY's, one has to be up and one has to be down. Just because I put the positives here, it doesn't mean, it could have been negatives here, it could have been whatever, as long as they're equal and opposite. Because this is, what's the law where every,
Forces.
third law?
Yeah.
Equal opposite. So BX and BY are the same forces because one is experiencing a push and one's getting a pull.
So if you ask us to draw one, we just draw them all positive. If you ask us to draw two.
If I ask you to draw one, you could draw them positive or negative. You could do whatever you want. But when you draw both of them, you have to make sure that they cancel each other out if they go together. So if I were to draw a free body diagram,
If I know that they go together, it really can't.
they have to cancel. So let's see, this is what, A, B, what's this, E? What's this? C, what's this?
D.
D, this is 100, 100, 100, 100, 200. This might be easier, look at this, do this. Shh, everybody look. Look what I just did, I put millimeters in parentheses, so I don't have to write it so many times. Okay, just put parentheses millimeters here, and then all the numbers I know. Okay, so when I put these two together, I have to draw, let's go off my drawing. My AX and AY are like this. My EX, they're positive. How about C? Do I draw a positive or negative according to my drawing here? You guys, which way, based on what I have drawn here, the directions,
Up.
what are these?
0.
Yeah, there's no, because it cancels out.
Well, I'm talking about point C.
But
I didn't connect it yet.
It's gotta be.
That's all I did is I connected this member with this
It's
member.
gotta be down to the
negative.
left.
It's gotta be in the negative, it's gotta be off of this, because I connected this member with this, right? So the CX and CYs is that one. Does everybody see it now?
yeah.
Okay, and what about D? We said it's a normal, right? So whenever you put two bodies together, you have to make sure that where they connect, they have no longer have the forces. Does everybody understand that the only reason this CX and CY are negative up on the board is because I chose to put negatives here? But Sarah, was it Sarah or Alani who put positives? You put positives. So Sarah put positives here for BCX for the C's. Then yours would be positive on your paper. Okay, so I put one axis here, and I'm deciding from now on I'm doing this with the mill. I don't want to have to write the units a bunch of times for dimensions.
M&M.
So now it says, how many unknowns are there if the problem only asks to determine the forces acting on member ABE? ABE. So how many unknowns are there? 6. 1, 2, 3, 4, 5, 6. So DJ, we're up to you. Let's call this free body diagram A, B, E, C, D, okay? So let's make the assumption that the question is asking us to find all the forces in ABE. Okay, so that's 6 of them. How many equations are we going to need? 6 equations. So if the problem says find all the unknowns in member A, B, E, we have 6 unknowns and we need 6 equations. Okay. But we have, how many free body diagrams do we have drawn? We have 5. Did we need all 5 of them? No. How many do we need?
2.
You need 2, at least. We need 2. But it's, I find it quicker to draw a free body diagram than do all the equations. So I don't mind drawing more free body diagrams than I need. But let's try to figure out, we want to figure out AX, AY, BX and BY, EX and EY. And we're going to try to do the least amount of math as we can. So DJ, looking at the free body diagrams, is there one equation we can do to find the A's, the B's, and the E's?
I don't think in one equation.
Let's see. So look at all free body diagrams.
AX equals -150.
Okay, how did you get that? Which free body diagram did you use?
I used the total.
Right. So let's use the free body diagram total, and what equation did you use?
Sum of the forces in the X.
Sum of the forces in the X gave you what?
AX.
AX. Does everybody agree with that? Okay, Kyle, next. How about another equation that we could find another one of those unknowns?
Pass.
Okay. Rachel?
I could do some of the moments around point T in the total one.
Okay, so pick the total free body diagram and do sum of the moments about D. And what's that going to enable us to find? AY.
Can you find AY by looking at the total free body diagram and see that there's only AY and pointing up, so AY would have to be the negative of the normal?
That's right, but we still don't know what the normal is, right?
Um,
Right, so the N would still be a normal. So everybody looking at the total free body diagram, do sum of the forces in the X and you get AX. Everybody agrees? Do sum of the moments about D and you could find AY. Agree? Okay, so far we have AX and AY done. So let's check them off. So check them off on the free body diagram. We figured those out already. So we figured out AX and AY, we figured out AX and AY. Okay, now we still need the B's and we still need the E's. Okay, where are we? Lonnie, we're up to you. Not allowed. Look at the free body diagrams, one at a time. Does anybody see another equation where we can find one unknown? Okay, so some of you do. So there's one there. Let's give a hint. Which free body diagram?
ABD.
Can find one ABD.
Okay, ABD, ABE rather. Does somebody see another one? CEF. So there are two free body diagrams that could give us. Wait. I don't think ABE can. Oh, yes, it can, of course. Okay, Lonnie.
If you do CEF and do a sum of the moments, you could do around E and get.
Yeah. So if we do.
Around C to get the.
Right, to get E.
X.
Right. So does everybody see that? Free body diagram CEF. We do sum of the moments about C, and it gives us an equation of EX with the 150.
Yeah. So
Put your hands up. Does everybody agree that we could find EX? by doing some of the moments about C. So we found EX now, and EX here. Okay, Santiago, another one?
From BCD,
BCD.
if you do some of the moments about C, you can find BY.
Well, we still don't know N.
Yeah, it's AY. Okay,
It's
Some
AY.
of the forces in the line.
From
in the
total.
Okay, but then we have to do it up here. Right? I think that's a great idea, but I'm trying not to find unknowns that I don't need to. And they don't ask us for N, so I'm gonna try not to do it. Let's see. So we still need BX, BY, and EY. Do you see an equation we could do?
Some of the moments about B to find EY.
So Chelsea's saying in free body diagram A, B, E, we do some of the moments about B, and we could find EY. Right? Now we have EY.
And now you can.
Santiago, I'm gonna go back to you now. We still need to find BX and BY here, right? So what can we do now?
Some of the moments about A.
Wait, hang on.
Some of the moments about A or E.
Right, but could we do an easier equation? I always like force equations. I think they're easier than moments.
So some of the forces in the Y,
Right? Give us
BY.
and we find BX.
Yeah, some of the forces in the X.
Some of the forces in the X find BX, and we never had to find N. But we had to use a lot of free body diagrams, right? So the question is, you know, it takes time to draw free body diagrams. So you have to personally figure out, do you like drawing more free body diagrams, or would you rather do more equations? So what we actually are working on right now is a frame problem. And if you look on the syllabus, here's frames. The frames are very similar to what we've done already, right? This doesn't seem any different. It might be harder, there might be more equations, there's more free body diagrams, but it's nothing new. So we're looking at doing a frame problem here. And typically on a frame problem, you want to draw a free body diagram of the total structure. And on a free body diagram, you want to draw a free body diagram of the one that they are trying to find members of. You should write this down. This is important. So on a frame problem, typically the most helpful free body diagrams are the total structure and the one where you find what when they're asking you for find forces in member whatever the member is in question, that one's the other one you want to do a free body diagram of.
So we might not always need all of them.
Right. So let's go back. I know somebody had a question. DJ?
I'm still just a little confused why you don't draw forces at U, E, and C, and then you did on, you
Okay,
did
say it
for
again.
the C.
Okay.
You don't draw on the total free body diagram?
Yeah.
Body diagram, I don't understand why
Sure.
you don't draw forces on E, B, and C.
Okay, so
And then on
why
the
do we not draw forces here, here, and here?
Because they cancel out, but on the pins.
They're pins, and the pins are experiencing a force, right? But when I could only analyze them when they're separated. When they're together, the force is inside, but it's internal to the system, and one force is going this way and one's going that way, and they cancel each other out. But when I separate them, they become external forces, and then I could find them.
So, why do you draw A then? The AF?
So because A, if you look here, A was connected to the ground,
Okay.
right? See, and this is the big thing that I need to talk to the physics department about, and this is a good thing for me to talk about it because I saw it on your quiz.